Okay, good evening everyone. This is going to be video number 4 in my linear algebra series. So it's been like a long time because I've had other things, commitments, so it's no longer the summer holidays. So I have things I need to get done, and entrance exams coming up. But I had a nice comment recently that made me want to get back into doing this. So I'm going to continue for, it will probably be on and off, the videos that I make, but I'll try my best to get as much of these done as possible for you guys. But yeah, basically, we're going to do some linear algebra. Today we're going to be talking about matrix multiplication. And it's probably something that you've met before in your sort of studies. Obviously, at this point, this is a first-year uni course, so I'm grabbing this from Oxford course notes. So if you're like, I don't want to listen to this guy, he's just basically talking about the Oxford lecture notes, then I don't blame you. And you can visit the lecture notes online at courses.maths.ox.ac.uk. But without any further ado, let's get into it. As I was saying, we're going to talk about matrix multiplication. And obviously, matrix multiplication is, if you're in the UK and you've done your A-levels, or probably the equivalent of A-levels in other countries, you would probably come across matrices, and you would probably come across matrix multiplication. But you might not have come across the formal definitions of matrix multiplication. The formal definition of matrix multiplication. What was more likely is that you probably just took the algorithm for granted. And you probably always ask yourself, why are we multiplying matrices in a certain way? And to a certain extent, we can answer that question today. Why have we defined? Because I mean, whenever you sort of multiply, for example, a matrix by a scalar, or a vector by a scalar, I mean, those are very sort of intuitive things that you're doing, right? You're just scaling up each of the components, even though that's sort of how we're defining it. In the same way we define matrix multiplication this way, so there's no like intrinsic. It's not like nature, which just sort of intrinsically acts in a certain way. Whereby like matrix multiplication has to be like this. It is a definition, but there is a motivation for that definition. And for the other ones, the motivation is just intuition, right? Like it makes intuitive sense for a scalar multiplied by a vector to just scale up each of the components. But for matrix multiplication, it's a little bit more interesting than that. We're not going to get to the full details today, and I think we'll talk about it later in the course. But hello, my cat has decided to make an appearance. Hello. But yeah, I mean, ultimately, you're going to need to come on. Come on. But yeah, I mean, ultimately, we'll talk about matrix multiplication and we'll prove a couple things, and we'll just make it very formal today. I do appreciate this is still relatively early on in the course, so you will have to give it some time to ramp up. It's a first year course as well, so obviously all that's really assumed here is A-level knowledge and potentially some A-level further maths knowledge as well. Because I mean, you would have only covered matrices in A-level further maths, right? Okay, so let me just try and write this stuff down. So we have a linear algebra. Linear algebra. Okay. So I'll put a straight line down here, and I'll put a straight line somewhere over here, which means that I don't like scribble everywhere. And this is hashtag number 4. This is video number 4 in the series. Okay. Right. So let's start by considering, we've already by the way spoken about what a matrix is, just like an array of numbers. So if you want to sort of go back to that, that's covered in my previous videos in the series. Okay, so we really do start from what is a matrix, things like that. And linear systems of equations in my previous videos. So if you are interested in that, and you're not sure, for example, what a matrix is or how you add two matrices, that's covered in my previous videos. Okay, so but we're going to start by assuming that you know what a matrix is, and at least informally, or to a satisfactory extent. And then we can say the following: we can say consider an n by n matrix. So obviously these are the dimensions of a matrix, right? So m is the number of effectively m is the number of effectively rows that you have, and then n is the number of columns, right? So if I have a 2 by 2, it's going to be... Sorry, I always get that confused because I thought for a second that it was... Because I had written that it was rows and columns, but for some reason I thought it was inverted, it was columns and rows. And I was like, wait, have I got this right? But yeah, no, m by n, so this would be 2, this would be 2. So that's a 2 by 2, and this was 2, and this was 3. Then this would be a 2 by 3 matrix, right? So an m by n matrix basically represents a matrix with m rows and n columns. Okay, so we're going to consider one, and we can actually write an m by n matrix. I believe we discussed in previous videos, just denoting it with a capital letter, and then writing these sort of brackets aij. So even though this is just sort of like it looks as if it's just one term inside a bracket, the fact that we have a sort of ij, the I and the j in there, effectively represents all of our possible components of our matrix, but condensed into sort of one sort of thing. So that we don't actually have to write out, because obviously in m by n, m and n are arbitrary, so it's slightly weird to write it out like you would normally represent a matrix. So instead you use this form. Obviously I, again, aij is the ijth component, so I is like sort of your row and j is your column. And so obviously we also have these restrictions, that 1 is less than or equal to I is less than or equal to m, and then 1 is less than or equal to j is less than or equal to n. Okay, but these are implicit. These should just be, I mean, whenever you see this, so those inequalities, just sort of, there's not really much else to it other than just that we effectively have m rows and n columns. Okay, if it was p by k, then that would be a p in the first inequality, I is less than or equal to p, and k in the second one, j is less than or equal to k. Yeah, so we have those inequalities, and we also have, I'm also going to consider a p by q matrix. So under p by q matrix, b is equal to bij. Okay, so we have these two matrices, and what we can say is we can say that we can only multiply matrices. So we can only multiply matrices if n is equal to p. Okay, so this is our first kind of rule, and you know, this is how you did it at A level, right? And potentially actually at GCSE Further Maths as well. So you know, how do you multiply matrices? Well, the first thing that you need to check is that you can multiply matrices, and you can only multiply matrices if n is equal to p. So if n is not equal to p, then actually the multiplication is undefined. I guess that's slightly annoying. But it's a caveat of the definition, right? This is how we're defining matrix multiplication. And as I said, there are reasons for these things, and we'll get into them. But for now, just know that we can only multiply matrices if n is equal to p. This should already be known to you, I think, because, like I said, A-level, GCSE Further Maths, you guys have been doing these kind of things, right? So if you have a 2 by 2 and a 2 by 3, you make a 2 by 3. If you have a 3 by 2 and a 2 by 4, you make a 3 by 4, right? These are just rules that you probably know. But for now, just know that if effectively n is not equal to p, so our matrix A is n by n, matrix B is p by q. If n is not equal to p, then we cannot multiply the matrices, it's undefined. Okay, so matrix A must have as many columns as B has rows, right? So have as many columns as B has rows, right? And that's what that's saying, effectively. N is equal to P effectively means that A has to have as many columns as B has rows. So if that helps you remember it, make it more intuitive, then that's the rule, right? Okay, so if this, obviously if that's satisfied, then we do have a product, and this product is defined in the following way. If the product exists, then we define it as a matrix. So when you multiply two matrices, you're going to get another matrix if it's defined as a matrix, and we'll call it capital C. So capital C is equal to capital A times capital B. Then we define it as C equal to capital A times capital B, which is an m by q matrix. So that's the first fact that should be sort of highlighting itself to you, is that when we multiply these two matrices, we get an m by q, assuming that n is equal to p. Right, so we have an m by n multiplied by an m by q, you get an m by q. So you just take the first and the last, effectively, parts of the dimensions. If you were to write like the dimensions of A and the dimensions of B, m by n, n by q, m by q. That's how it works, right? It was A by B, B by C, A by C. That's A by C is the matrix, the dimension of the matrix, the resultant matrix that you get when you multiply those two matrices together. Okay, A and B. So that's the first thing. But obviously, what even is this matrix? Like, I'm telling you it's an m by q, but how am I supposed to figure out what the components are? So we need to also give that information, otherwise it's useless. So, which is an m by q matrix defined. I said, okay, so what did I say? We find it as a matrix, which is an m by q matrix with components given by, right, Cij. So this is going to be a bit weird when you first see it, if you've never seen this formal definition before, but it's going to have to be a definition that you know for now. Okay, so it's a sum from k is equal to 1 to n of aik, bkj. Okay, so this is effectively how you can compute the entries of your resultant matrix. So we actually take this formula for granted at A level. We don't necessarily, actually I think my teacher did actually introduce matrix multiplication just via this formula, but you don't need to know it because you can just, you know the algorithm. So you just, whenever they ask you to multiply two matrices, similar for GCSE Further Maths, you probably didn't like memorize this formula, right, which is really what's happening, but instead you probably just knew the algorithm and computed it. This is what people say, right? A level is just kind of algorithmic in many senses, that it requires you to do things and not necessarily understand them in the full depth that you would at university. But this is matrix multiplication, right? I mean, it's not that exciting, right? It's just a sum. What is it a sum of? Well, aik is the ik component of matrix A, and bkj is the kj component of matrix B, and obviously we're varying k from 1 to n, okay? So it kind of sometimes helps. In this case, it's still a bit daunting to do it, but you can obviously take away that sort of symbol, and you could write that as ai1, b1j, add a12, b2j, add a13, b3j, all the way up to add a1n, bnj. Okay, that's just the same thing as that sum. It's more compact to write it like this, but it's also a little bit more daunting. But you do have to get familiar at this stage in your sort of mathematical career with the sigma symbol, right, with the summation symbol. If you don't like it, you're gonna have to sort of put up with it, because I have a feeling that it will show up a lot more. Okay, well, I'm obviously no expert. Right, okay, and obviously we also still have that 1 is less than or equal to I is less than or equal to m, and 1 is less than or equal to j is less than or equal to q, sorry. Because it's an m by q. Okay, so don't write n again there, because it's not an m by n this time, is it? It's an m by q. Okay. Right, but I mean, this is, I mean, even though I've told you necessarily, like, this is how we defining the IGF component, it's probably still a bit weird, so it's best to look at this with an example, okay? Because it's probably, you're probably still like, well, okay, I know how to multiply matrices, but what is this formula telling me? And why are we you know, deeping it in a sense? Why do we need this? Well, I can answer that question immediately. Why do we need this? Well, we need this to be more precise. Okay, mathematics is not just about algorithms and computing things. It's about being precise about what you're really doing, and this will also help us prove things. Okay, so an algorithm, like just the general process, is not precise enough to prove anything, right? It's just it's a process, which we know how it works, but like it's not concrete, right? It's more just like in your head, you know how to multiply them. But like if I was like, prove this, you would probably be able to use the algorithm to prove it, but it's not really a proof in many ways, because you're not really kind of just doing something that's sort of not really defined. I mean, I guess you could define it for the proof, but it's just a lot easier to prove things with this sort of more compact form here, because it's the same thing. But like the other way, there's no real. This is the compact way to write what you're doing. Whereas in the other sense, you're just kind of doing it. You're not really writing it out in a compact format. So it's, I guess, easier to follow proofs. But to be fair, this also kind of complicates proofs. So yeah. Anyway, let's look at an example. So if I have a matrix A, which is 2 by 2, and it has these entries 1, 2, 3, 4, and I have a matrix B, which is given by these entries, so 1, 2, 3, 4, 5, 6, so it's a 2 by 3, right? So we can obviously, so C, which is effectively the resultant matrix, when I multiply those two matrices together, is defined. Okay, why is it defined? Again, because the number of columns is here is equal to the same as the number of rows here. Okay, so 2 is equal to 2, n is equal to p, okay, which is equal to 2, right? And so then we know that the product will exist. So then the next question is, what actually is that product going to be? Okay, so we can figure it out if we do some algebra, I guess, some summing. Obviously this is just going to be equal to the sum, so from k is equal to 1, right, to n, so in this case n, right, is going to be equal to 2, right, because n is equal, so we had m by n, and p by q, well n by q because p is equal to n, so m by n in this case is a 2 by 2, so n is equal to 2, of effectively a, I, k, b, k, j. So this is just the same thing as a11, no, sorry, ai1, b1j, add ai2, b2j. Okay, so this is effectively how we will compute the entries of our resultant matrix C. Okay, and so C, obviously we can also tell by our definition, that is going to be a 2 by 3 matrix. So C is a 2 by 3, so we keep that in mind. So in total we're going to have 6 entries, right? So the entries are always given, the number of entries is given by the multiplication of those two numbers, which is potentially also why we have that symbol there, right? Because that gives us a number of entries. 2 by 3 gives us 6 entries. Okay, so we're going to have 6 entries. So obviously those entries will be given by A11, sorry, actually I should write as C, C11, C12, C13, right? C21, C22, C23. So you can have a go at computing these. I'm just going to go ahead and compute C11. So obviously C11 is equal to A11, B11 plus A12, B21, okay? Which we can just go and we can have a look at this. So we just take this row and this column, right? And we do 1 times 1 plus 2 times 4, right? So that's actually going to be 1 plus 8, which is 9, okay? So this specific term inside my C matrix is 9, okay? And since C is a 2 by 3, we're going to have it like this. So these are going to be 2, this is going to be 3, and C11 is 9, so this element here is a 9. And then obviously the rest you can figure out, right? Using the exact same definition. But you can see now exactly how this is working, hopefully, and how it links into probably the algorithm that you've just kind of mindlessly, maybe not mindlessly, but you've just been using in A-level, okay? So that's the connection that I wanted to effectively make. Awesome. Okay, well, we can also actually represent this product in a different format, which will be useful. If we write, we can write the rows of our matrix A as row vectors, right? So R1, R2, all the way up to Rm, right? So we have, it's n by n, so we have m rows, so that's why I'm going up to Rn there, okay? And we can write the columns of B. You'll be thinking, why do I care about the rows of A and the columns of B? I'll explain that in a second. So we can write the columns of B as effectively C1. So these are column vectors, right? So it goes all the way up to CQ, okay? Because B is P by Q, right? So you have Q columns, Q columns, sorry, and rows, it should be like that, but whatever, you guys get what I mean. So that effectively ijth entry of the resultant matrix, when you multiply the two matrices A and B together, is given by Ri dotted with Cj, okay? For 1 less than or equal to I less than or equal to m, 1 less than or equal to j less than or equal to q. Okay, so these facts here, as I said before, you don't really need to worry about them too much. They're just saying that you have m rows and q effective columns, right? And the reason is because effectively the resultant matrix C, when you have an m by n and an m by q, and an m by q will be an m by q. So C is going to be an m by q, and so it's going to have m rows and q columns. That's all this information is saying, really. And obviously you can't have 0, I mean, because you're choosing the ijth entry, right? And so we define it to basically I to start at 1, right? Because it's like the first row, first column, so I has to be greater than or equal to 1, so j has to be greater than or equal to 1. So that's all that's saying. But the more interesting part is that dot there. So you're probably familiar with the dot product from A level. If not, then let's try having a look at what this is. Well, as I said, this is called a dot product. Okay, so the dot product basically takes two vectors and spits out a scalar or a number. And how does it do that? We need to define what actually happens. I'm not going to define it here. There actually is a separate course in geometry. We'll define that if you're interested in that. I might make some videos on that in the future at some point. But dot product is just taking two vectors, spitting out a scalar or a number. And the way we get that number is by effectively writing these two matrices. So 1, 2, 3, 4, and then that's equal to A. We could say, and then B could be equal to 1, 2, 3, 4, 5, 6. And then we take the row of A, so the first row of A, for example, just, we could take either row, but I'm taking the first one. And we can take any of the columns of B, let's take the first one, and we dot them, okay? So effectively what we're doing is we take this row vector 1, 2, and we dot it with 1, 4. And the way that that's defined is effectively by taking the first component of each of the vectors and multiplying them, and then adding the second component of each of the vectors, multiplied together. So effectively this, dotted with this, is just going to be 1 times 1, add 2 times 4, okay? Which is just 1 plus 8, which is 9. Okay, which is the same thing we got via just the sum definition. Okay, so the two things are equivalent, and if you want, you could think about it as that dot product between the rows of matrix A and the columns of matrix B. But it's up to you. That might quite overcomplicate it. But you need to sort of understand these now. Okay, you're at a point where you sort of should understand the sort of really what's happening as opposed to just how to do it. Okay, like I know that it seems potentially pointless, but to an extent, this is the sort of base here, right? And probably later on, you're going to come across things that you haven't met before, and you need to be confident with, just sort of these sort of more rigorous ways of defining things, and yeah, I mean that's basically it, right? And in this sense, with defining matrix multiplication more rigorously than you're probably used to, but it's important for proofs, and it's important just for your general mathematical maturity. Okay, so overall, it's necessary at this point in time. Okay, right, very good. I'm gonna turn on my fan. It's actually boiling in my room for some reason. Okay, I hope you can still hear me though. Yeah, awesome. So let's sort of talk about matrix multiplication even more. So let's think about this, right? So like a natural question after we define matrix multiplication is why have we defined matrix multiplication that way? To an extent, I'm not going to be able to answer that entire question in this video, but I will be able to answer parts of that question in this video, okay? And I will be able to give you some intuition as to why this definition is useful, because at this point in time, it probably seemed arbitrary. It probably has seemed arbitrary your entire life up until this point, and in some senses, I think it is, right? It's a definition, but also there is a reason for this definition. Okay, so let A be an m by n matrix, and also let B be an m by p, so that obviously the resultant matrix AB is m by p. Okay, so this should now be known. Okay, you should now understand that this is how matrix multiplication works. Right. So this is fine. This is just what we've been talking about. What I can now add on is this. So if V is an m by 1 column vector in, we say Rn col, like this, to effectively mean the set of all column vectors with n components in. So it's a set, right? So I could also have said this. So I could have put V as an element of that set, right? That's also fine. So if this is true, right, if I take a column vector in my set of column vectors with n components, then what I notice is that the matrix A multiplied by that column vector is, again, so you're still multiplying two matrices, right? Because this column vector is a special type of matrix, an m by 1 matrix. So every vector is a special type of matrix. Okay? Then AB is obviously going to be an m by 1 column vector, right? If you're wondering why this is, well, just think about how we define matrix multiplication, right? That's what we really need to think about. A here is an m by n, okay? And V is an m by 1. So when you multiply two matrices, you're going to get m by 1. As simple as that, right? So effectively, so that obviously what we can say is that AB is an element of R col R. Okay, simple as that. It's natural then to define a mapping. Okay, so we define a map. We call this map L capital A from Rn col to Rm col. Okay, so we're just mapping effectively a n by 1 column matrix to an n by 1 column matrix. Okay, and I think we'll definitely talk about these sorts of ideas, this sort of mapping. You probably already have seen at A level that matrix. You can use matrices to represent effectively transformations and things like that, right, in the xy plane. And we can extend those ideas, right, in linear algebra. So we'll definitely talk more about maps. But for now, just think about, effectively what this is saying is you're taking an n by 1 column vector, and what you're doing is you're mapping it, you're just changing it effectively via this. When you basically multiply it by A, you're mapping it, or you're just sort of taking it from that n by 1 to the n by 1. Okay, that's what you're doing. That's why it's a map, right? Because once you apply this matrix to it, you multiply it by this matrix, you're going to bring it to this n by 1 form, to this new set. Okay, so it's a mapping. Right. And mapping should be natural ideas, by the way. So if they're not, then I would definitely take a look at some sort of introductory university material, because I think most universities talk at an introductory level about proof writing, functions, relations, sets, those objects. Those should be very, 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 at least at a basic level. Like, you don't need to know, obviously, like set theory in most advanced forms, but like at a basic level, they should be pretty much second nature to you at this point in time. So a mapping as well should be pretty self-explanatory. But I mean, it is self-explanatory, right? You're taking an n by 1 column vector, and you're taking it and you're making it an n by 1 column vector by applying the A matrix, multiplying it, by multiplying the column vector by that A matrix, right? The matrix A. That's pretty much all we're doing, right? So by similar reasoning, we can define a map via similar reasoning. We can define a map, right? We'll call it LB, from our P column, so the set of all column vectors that are P by 1, to our N column, so to the N by 1 column vectors. And it's going to be the same idea, except this time we're taking a vector V, which lies in the set of all column vectors with P components, and then we're multiplying it by the vector V, right? So this is obviously going to imply that BV is an element of Rn col. That's all we're doing here, right? We're doing the exact same thing, but instead of multiplying it by the matrix A, we multiply it by B, right? So we can also identify this map from the column vectors with P elements in them to the set of column vectors with P elements in them to the set of column vectors with N elements in them, okay, or N components. So we have this other mapping here, LB, and what's going to be the most interesting to us is the mapping LAB. So you might think, what does that mean? Well, LAB is effectively just us multiplying a column vector V by the matrix AB, okay? What we can do is we can define a mapping, or I should say a map, LAB from our P col to our M col. Okay, so first of all, A is M by N and B is N by P, right? So AB is going to be M by P, so that's the first thing that you need to know. So AB is M by P, right? And effectively, if we take a vector V, which lies in the set of column vectors with P elements in it, and we multiply this, so this implies, and we multiply this by the matrix AB, right? Or we call that C, then effectively AB multiplied by that column vector V will indeed lie in the set of column vectors with M elements in them, okay? And the reason for this is because AB is M by P, right? So when I multiply an M by P matrix, because AB is just another matrix that's formed by multiplying two matrices, when I multiply an M by P matrix by a column vector V, or by not even a column vector, well, I mean, yeah, a column vector, but it's going to be a P by 1 column vector, so M by P, P by 1, you get M by 1 is your resultant there, right? So, which an M by 1 is just a column vector with M elements. So you can see how this mapping is working, right? We're taking a vector, column vector, in the set of column vectors with P components, multiplying it by this matrix C, which is defined as AB. And we're getting a resultant column vector in the set of column vectors with M elements, okay? That's all that's happening here. And you might be wondering, though, like, why is this explaining why we have matrix multiplication, like why we define matrix multiplication the way we do? And that's a question. And it's because of sort of something, an observation that we can make when we consider sort of these maps, okay? And that observation is exactly that LAB is effectively the same as LA composed with LB, okay? So this is, should we say, yeah, I mean, this is the observation, right? So this is like an observation. And, you know, this is really as a result of the way that we define matrix multiplication. And this is nice, okay? But let's think about, first of all, what this is really saying, okay? So effectively, whenever we take this mapping LB, so LB is going to take a column vector in this set RP col and map it to a column vector in the set Rn col, okay? So effectively, we're going to end up, when we map a column vector from RP col to Rn col with an M by 1 column vector, right? And then we compose that with the mapping LA. What that means is that we effectively take then that M by 1 and we map it through LA to an M by 1. So N by 1 to M by 1. I know that's similar. It might not, you might not make out the difference in my voice because the fan is on and etc. But it's an n for Niagara Falls by 1, and you're mapping that to an m by 1 for marbles, right? Okay, so hopefully that's clear. So you're doing LB first, and then you're taking the product of LB, which will be an m by 1, n by 1, and you're effectively mapping it via LA to an m by 1, okay? And that is the same thing as just effectively doing one mapping, which is just LAB, because LAB takes you straight from our P-call to our M-call, which we can do either via a 2-step mapping, a composition, or via a 1-step mapping, okay? So that's what this is saying, and that comes out neatly as a result of the way that we define matrix multiplication. Okay, so this is nice, we will sort of talk about it a little bit more later when we get back into mappings and things like that. Okay, but these ideas are pretty much central. Well, they're very sort of, I think, crucial ideas in linear algebra, and it's nice that we have this property, this composition here, that comes as a result of the way that we define matrix multiplication. Okay, awesome. Just making sure I said everything. Although this is also equivalent to saying the following. Okay, so it's equivalent to me saying AB multiplied by B is the same as effectively A multiplied by BB. Okay, so because obviously LB is doing this, and then you compose that with LA, so you're doing A multiplied by that, and LAB is just this. So that's this observation is saying the same thing as this. So this is technically also a proof, although also doing a different proof using the definition of matrix multiplication, that matrix multiplication is associative. Okay, so associativity of matrix multiplication. You might think, what does it mean to be associative? Well, it means exactly as I've written there. That effectively we can exchange those brackets and the result will not change. So I can move the brackets from AB to BB, and the result does not change. So this is the associativity of matrix multiplication. Okay, so in other words, our definition gives us this property that matrix multiplication is associative, and it links to this idea of compositions of composition of maps. Okay, which we will also come back to later on. Awesome, so hopefully that's clear. If not, don't worry too much, we will come back to it, but I think it's nice to have the intuition behind that. I tried my best to give a good explanation. Okay, so now let's talk about a definition. So definition, right, so we define, so let's talk about the identity matrix. Again, another object that you're really familiar with, how we need to define it. So what is it? So we define the n by n, right? Because every identity matrix you've dealt with probably so far is going to be an n by n identity matrix, right? Kind of has to be an n by n identity matrix. We define the n by n identity matrix, and we'll label it sort of with this capital I subscript n, okay? As an n by n matrix with entries. So obviously we know it's going to be an n by n matrix, but what is actually going to be inside that matrix? Well, as you're probably familiar with from A-level, and maybe even GCSE further maths, it's going to be ones along the diagonal, effectively. So you look at your sort of diagonal, your leading diagonal, and it's just going to be filled with ones. But what is that? What is that? Like, how do we sort of quantify that? How do we put that into sort of more rigorous, more precise terms? Well, we can do it in the following way. We can say that the ijth term, the ijth effectively entry of our identity matrix, our n by n identity matrix, is just delta ij is equal to 1 if I is equal to j, and 0 if I is not equal to j. So I want you to just sort of stop the video here and have a think about that, right? What is that saying? Just very quickly, if I take I2, which is going to be a 2 by 2 identity matrix, right, then effectively it's going to look like this, 1, 0, 0, 1. So this component here, that is the ijth component where I is equal to 1 and j is equal to 1. And this is the ijth component where I is equal to 2 and j is equal to 2. This is going to be 1, 2. This is going to be 2, 1. And you can see, when these numbers, I and j, are equal to each other, then you have a 1. Else you have a 0, okay? And you can verify this for, effectively, the sort of 3 by 3 identity matrix, 4 by 4, the ones that you're familiar with from A-level, they all follow this rule, okay? So we can effectively quantify the entries of our identity matrix using this delta here. And the reason why it's a delta, well, I don't really know why it's a delta, but we do have a name for it, which effectively fits the fact that it's a delta, which is called the Kronecker delta, okay? So, so we say that delta ij is known as the Kronecker delta. Okay, so that's probably something we've never seen before, but it's a very simple idea. The idea of the Kronecker delta is just effectively this piecewise defined thing that takes in these two inputs, I and j, and spits out either 1 or 0, depending on whether I is equal to j or I is not equal to j. Okay, and it's important, okay, in linear algebra, so we're introducing it now. But you probably haven't met it before, because again, before you never had to really think about what's going on behind the scenes. You had to just do things, okay? Now we're thinking about what's going on behind the scenes, and we're writing things out more rigorously, okay? And this is important in doing that. Okay, this is the Kronecker delta. Right, and also in general, we often denote the identity matrix, so obviously you can see I've written it up here as IN, but sometimes you also see it written as I, so there might not be a subscript, okay? And in that case, we don't necessarily, I mean, it will obviously be implied from context, right, what the size would be, but if it's just I like that, then I assume that it would be holding for all values of n that are acceptable, right, so from 1 to basically anything, right, any positive integer n. So unless we really care about a specific identity matrix size, so like I3, if we care about the 3x3 identity matrix, we'll write I3. If we care about the 2x2 identity matrix, we'll write I2. But in any other case where we don't care about the size, we'll just write it as I, okay? So you should also be familiar with that. If you, for example, see someone write I, it's not a mistake. They haven't forgotten to write I3. They just don't care about I3 specifically. They care about probably all sizes of identity matrices. Matrices. So that's that. Also, obviously, notation in these things varies from, really text to text, right? So, in these notes that I've taken this from the Oxford Notes by Richard Earl, he's written it with I subscript n like this, but maybe someone else will write it differently. Although I think in general this is, you typically represent identity matrix with I, right? Like identity I makes sense, but you never know, right? And technically it's open, you could do it however you wanted to, but there is a general sort of standard, there is a general sort of, idea of how we should represent these things. And so typically I think it is represented with an I, but, and it is represented in this form typically, but obviously do expect in general with maths things to change as you sort of read different texts and different things like that, but hopefully it should be obvious via context what people are talking about if the notation has changed. Okay, so there's an important property about the Kronecker delta which we also need to talk about and clarify now. So if I have n real numbers, right, and I have this property that I have this k, so I'm defining a k to be some basically real number, well, not real number, some positive integer between 1 and n, right? Because they're like my indexes, and those indexes are positive integers. So k is just some positive integer between 1 and n, right? So we can write that with this z plus here. So if I have n real numbers, x1 to xn, and I have this positive integer k between 1 and n, then in general, right, then we have this fact that the sum from I is equal to 1 to n of delta ik xi is simply equal to xk, okay? And you might wonder, why is this? And you really need to be confident with the definition of the Kronecker delta to really understand why this is true. Okay? But remember, the Kronecker delta is going to be 0 all the time, pretty much, unless we have this one condition, that I is equal to j. So in this case, k is fixed, right? And we're looping through values of I in our sum. So as soon as I becomes k, you'll get delta kk xk. This will be 1, and this just gives you xk, which is this. But in all other cases, right, because there's only one value of k between 1 and n, in all other cases, delta ik is just 0. So you're just doing xk plus 0 plus 0 plus 0 plus 0, all 0, right? So it's going to give you xk at the end. So this property is important, and actually not too difficult if you really think about it, right? But this is the way of writing it. And we call this property the sifting property of the Kronecker delta, okay? So it's one of the, if you were to sort of analyze the Kronecker delta, this would be one of the properties that you probably would want to take out of that, right? Which is that it basically abides by this rule, by this sifting property, okay? Which is useful, okay? So I think we'll use it even in one of the proofs today, which we're about to do, to finish off. Okay, so this is this. So yeah, this is the sifting property of the Kronecker delta. So sifting property of the Kronecker delta. Okay, awesome. So now let's do some proofs to finish off, right? Regarding matrix multiplication. So first of all, so let's, I'll say this as a theorem, although most of these are really lemmas, they're sort of smaller results. Theorem is typically regarded as a big result. I guess these are all big in some sense because they're quite crucial. Central to just linear algebra and matrix multiplication in general, right? You should know these. But they're not really extensive proofs, right? Like they're just sort of short proofs that rely on the definition of matrix multiplication. So they're really kind of lemmas, but I'll write them as theorems, okay? I'll be slightly lazy, I mean, yeah, whatever. So the first theorem here is as follows. Let A be an m by n matrix and define L and P to be positive integers. Okay, that's what that sign there means. L and P, they're just positive integers. Okay, then we have these four rules. Okay, A multiplied by the n by P 0 matrix is the m by P 0 matrix. Okay, had to get that right. And then we also have that 0, the L by M 0 matrix multiplied by A is equal to the L by N 0 matrix. Okay, so those are the 0 matrix rules. 0 matrix rules. Okay, I think we did introduce a 0 matrix previously, just a matrix of zeros. Okay, pretty standard. And we also have these two other rules. Okay, so the third rule is that matrix A multiplied by the n by n identity matrix is just A. Okay, just spits back A. And the fourth rule, fourth and final rule, is that the m by m, okay, because identity matrix is always n by n or m by m, right? Multiplied by A, again, just spits back A. So these are just the identity matrix rules, so identity rules. Okay, so these are very standard rules, and you don't even really need to prove these things, okay, but it's a nice place to start in terms of proofs. So let's get started with proof. So number one, consider the sort of ijth element of this product. Okay, so A 0 NP, and this means that M by P zero matrix, right? Obviously, this is M. What do we define A as? M by N. So M by N multiplied by M by P gives you an M by P. Okay, so obviously you already know that the resulting matrix is M by P. Now all we have to do is prove that it will be the zero matrix, which is simple to do. So this is just going to be equal to the ijth element is just this ij, which is basically by definition equal to the sum from k equals 1 to n of aik 0 kj. Okay, this is matrix multiplication, right? This is how we define matrix multiplication. And in this case, we're just multiplying the matrix A, which has components aij, with the matrix, the zero matrix, which has components 0 kj, right? And effectively, this clearly this sum is going to be 0, because this is always going to be 0, no matter what, right? Every element of the zero matrix is 0, so this sum will just be 0 plus 0 plus 0 plus 0 plus 0, okay? For basically all values of I and j that we care about, it's just going to be 0, right? So, yeah, as simple as that, really. And it's sort of by definition, right? Like, there's not really anything else you kind of need to say here, because the zero matrix is just full of zeros. So you can sort of say by definition the zero matrix is defined as a matrix of zeros, or however else it was written in the notes. Okay, if you want, you can go back to the notes and be particularly rigorous about that. But most people, they can just accept this, right? That effectively a zero matrix is full of zeros, right? So as long as the multiplication is defined, which it is, then effectively this sum is just zeros times some other number we don't care about, right? It's just 0. So every term of the sum is 0, so the entire sum is 0, right? Because 0 plus 0 plus as many zeros as you want will still give you 0 for all values of I and j that we care about. So it's always going to give us 0. So now we've shown rigorously that this is going to be the zero matrix, because every single component is just going to be 0, right? I guess we're fixing I and j each time we evaluate the sum, right? So we're not looping over I and j. Others have to do other sums and things like that. We're not looping over those values. Okay, we're just fixing I and j and then evaluating the sum. So if I care about like the 1 1, the sort of element 1 1, then I fix I is equal to 1, j is equal to 1, and then evaluate that sum. But I'll still get 0, because I'm always every element of my zero matrix is 0. Okay. So now we have a zero matrix, and we know that it's going to be m by p, right? So zero matrix. And it's going to be m by p, so a 0 mp is equal to 0 mp, right? As required, right? And so number 2 is exactly the same argument. Okay, so similar. I say similar. It's literally exactly the same. Okay, you're just doing it the other way around. Okay, 0 lm times a. Obviously, you need to be aware of the dimensions that the product actually exists. It's the same idea, except you're just going to swap these two terms around. Okay, and it will be a slightly different sum, right? Because it's going to, instead of from k is equal to 1 to m, it's going to be what's it going to be? We have a zero matrix, which is going to be an L by m, and A, which is going to be an m by n. Okay, so I believe that it's going to be from k. Well, I guess you could still use k, right? I think it's going to be from k is equal to 1 to m, right? So the sum will be slightly different in that case, but effectively it's the same idea, because obviously the zero matrix will always just be full of zeros, and so the total sum will be 0. Okay, so 2 is exactly the same argument. Okay. Okay, then 3 is a little bit trickier, but still doable, right? So 3, I'm going to say consider the ijth element of our matrix product AIN. So the A, matrix A multiplied by the n by n identity matrix, that's just going to be equal to AIN subscript ij, which by definition is a sum, right? This is matrix multiplication from k equals 1. Do I mean to m there? Because I've written from k equals 1 to m. I'm not sure if I mean that, because I'm going to get an m by n. Do I mean that? Right, sorry, I just wanted to check, because I miswrote this in my notes, but it's going to be from k is equal to 1 to n, effectively, of delta ik multiplied by akj. Okay, this is just a definition of matrix multiplication, right? Well, I guess actually it should be the other way around, shouldn't it? I fumbled this completely. It should be aik, sorry, multiplied by delta kj, if you want to be specific, right? Because we do the first, effectively, matrix first, so that's going to be, we always put the first matrices components, first in the sum. So if it's a before in, then you write aik first, okay? That's actually important, okay? So don't, like, fuck that up, okay? Because as we'll see, matrix multiplication is not commutative, so matrix A multiplied by matrix B is not the same as matrix B multiplied by matrix A, okay? So do not mess that up like I did in my notes, okay? But effectively, you just get this sum, Obviously by the sifting property of the Kronecker delta, this is only ever going to be 1 when k is equal to j. So in that case, we just get this to be equal to aij, okay? Which is exactly just the matrix A, right? Effectively, each component of our resultant matrix AIN is just the same as the component of A, so it just is A. Okay, so AIN is equal to A, right? Simple as that, right? And also because obviously m by n multiplied by n by n is m by n, right? So A is just m by n, like, so the dimensions of A have not changed either, so it literally is just A again. Okay? Very good. All right, now number 4, if you go back to it, it's literally the same as number 3, just flipped, okay? So in that case, you sum from 1 to m, right? So your sum is going to be from k is equal to 1 to m, and this time you do the other way around, so delta I, ik, a, kj, okay? So make sure you do that properly. And you still get the same result though, right? It'll still be a, so it actually doesn't matter in this case, okay? So it is commutative in this case, but don't take that for granted because it isn't in general, okay? So 4 is similar, in fact it's the same argument, okay? So if you want to try that out yourself, I do recommend that you do that. Okay. Right, and then we have another theorem here, which is that matrix multiplication is not commutative, okay? So matrix multiplication is not commutative. Matrix multiplication is not commutative. So matrix A multiplied by matrix B is not equal to matrix B multiplied by matrix A. Okay? Do not think that. Do not think that. You'll get everything wrong. Like, not everything, but you'll get a lot wrong. You know you're doing anything there. Okay? This is crucial. Absolutely crucial. You probably know this already from A level. It's so crucial, you probably already know. Right? So just know this. Okay? It's not like algebra with numbers, like arithmetic, where you've just been doing 3 times 4, 4 times 3 the same, 12. It's not the same. Okay? It's different. This is one of the caveats with linear algebra, is that it doesn't behave as nicely as we expect it to, because of the way we define it, to be honest. But again, there's reasons why we define it that way. So we can't have everything we want in every system, okay? We have to make some concessions. We have to just deal with the fact that it's not commutative, okay? And that's fine, right? We don't need it to be commutative. There's no entity that says you shall be commutative for all, like, for everything. It doesn't need to be that way, right? So this is fine. But can we prove it? Well, the proof is simple. Just the proof is by counterexample, right? If we can just find a counterexample, then we're done. We know matrix multiplication is not commutative. So the proof is by counterexample. Right, so this positive counterexample I did. I took A is equal to 1, 0, 0, 0. And whenever you have a counterexample, try and keep it as simple as possible first, and then look for alternatives, which might be more complicated. So this would be A is equal to 1, 0, 0, 0, B is equal to 0, 0, 1, 0, okay? Then clearly, AB, when you multiply it, you just do the dot product of that of each row here with the column dot product with the column of B, right? So you can do 1, 0 dotted with 0, 0 just gives you 0. So that's going to be a first element. Then 1 plus 0, so that's going to be a 1. So 1 times 1 plus 0 times 0, 0 times 0 plus 0 times 0, 0 times 1 plus 0 times 0. So that's AB, 0, 1, 0, 0, okay, which is exactly the same as B, okay, just as a fact here. But that's irrelevant. And BA, if you just do it, is going to be, what you're going to get is, well, let's do it, just to make sure you believe me, and I didn't get it wrong. This is going to be 0 times 1 plus 1 times 0, so that's going to be 0. 0 times 0 plus 1 times 0, 0, right? And already it's different, right? Already it's different because it's not 1. Okay, that's really all we really care about. They're just different matrices, but let's finish it. 0 times 1 plus 0 times 0, 0 times 0 plus 0. So you actually get the 0 matrix, okay? This is equal to the 0 matrix, okay? So it's a 2 by 2 0 matrix. But yeah, as you can see, the main thing here is that AB is not equal to BA. So matrix multiplication is not commutative, okay? So matrix multiplication is not commutative. Is not commutative, okay? Very, very crucial fact there, okay? Right. Cool. That's that. Now let's have a look at another theorem. We'll just look at a couple more. This theorem says matrix multiplication is actually associative, which is technically already proved. So matrix multiplication is associative. So it's not commutative, but it is associative. So at least we get that from our definition, which is good. We already kind of spoke about this. Yeah, we can effectively prove it like this as well. So for matrices A, B, and C, which are M by N, M by P, and P by Q, respectively, we have that A multiplied by the product BC is equal to AB multiplied by C. So we can exchange these brackets and the result stays the same. That is just what associativity says. This is also true in arithmetic as well, right? So that is a parallel that you can make. Right, so if I have 4 times 3 times 2, so 4 times 6 is the same as 12 times 2. Right? So 4 times 3 times 2, you can group the 4 and 3, or the 3 and the 2, doesn't matter which way you do it. You're fine. Okay? So let's prove it. This is a little bit of an annoying proof. Not really annoying, but just slightly, you need to get used to the sums and things like that. Because naturally there's a sum because of the fact that we defined our matrix multiplication as a sum. So yeah, we have to deal with those. So we're going to start this by saying consider the ijth element of A, B, C, right? Which is just going to be A, B, C, ij, which is simply going to be the sum from k equals 1 to n of A, ik, right? Because A comes first, multiplied by B, C, kj, okay? That is correct, because BC is going to be n by q, because we have an n by p, a p by q, we have an n by q, and A is going to be an n by n, so that's fine. So this is the correct way, the correct translation of the definition. So make sure you always get that. So the top number here is going to be n, because that's the same as this here and this here. Okay, so make sure that you get that correct. And also make sure you get the order of these two correct. Those two things are very important, okay? It's just because otherwise you're just not translating the definition correctly, okay? So make sure you're doing that correctly. But you can pretty much, you know how that's going to work in general, right? With enough practice, it's pretty simple. So this is the definition, but it's still not helpful because we still have this product of two matrices in here, so we have to unwind that as well. So this actually just gives us sum from k is equal to 1 to n of aik multiplied by the sum from, we'll call it L, just to not get confused with the k, L equals 1 to p of bkl clj. And the p there is simply because b is n by p and c is p by q. So we always use this number here for the sort of upper index of that sum, right? So that's why there's a p there. Yeah, that's important. Now, what we can do, you can actually just try this out yourself and show this is effectively the same as just a double sum. Okay, so it's just literally a double sum. So we can move the aik in here. So this gives aik bkl clj. Simple as that, right? That's what this is. So that's what we obtain when we do that sort of sum. This is the definition of that product of matrices. Okay, this funky R double sum. Okay, I know it looks funky, but you don't need to worry too much about specifics. You need to know that we can get from this step here to this step, okay? And you can verify it by literally like dealing with the sum. This is going to be bk1 c1j plus bk2 c2j, so on and so forth, all multiplied by aik, right? So effectively, when k is equal to, so effectively it's going to be multiplied by what? ai1, right? And then it's going to be plus all of that ai2 plus ai3 and so on and so forth. And you can see that effectively, for each value of k, right, you're effectively just going to be able to bring the aik into that sum and just treat it as a double sum effectively. Yeah, so effectively you can verify that yourself. Just to make clear what I also mean. I mean, you have bk1 c1j plus bk2 c2j, add all the way up to plus bkp cpj, right? And you're multiplying this by aik and you're summing over all values of k. Okay? So this is just going to be equal to ai1 multiplied by all of that, b11, c1j, blah, 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 and then add a12 multiplied by that. But you can see that you can just distribute the a's into those brackets, right? And so you can just write this as the same as a double sum. That's what I'm doing, but I'm doing it in one step. Because otherwise I have to sort of justify it, and that's sort of slightly annoying. I mean, it's not really, because it's pretty simple, right? Like, it's clear that it does work that way. It's a finite sum, so we don't really need to worry about that, right? Finite sums, we can just do this. But yeah, I guess if you wanted to, you could write it out and convince yourself. Okay. Now, well, we're not done though. We need to also show this is the same as AB, the product AB, multiplied by the matrix C, right? So now we consider that. Now, consider the ijth element of this product, AB multiplied by C, right? Which is just AB multiplied by C, ij, which is equal to the sum from L is equal to 1 to P, okay? Because remember, in this case, when we do AB, what are we going to get? Well, AB is n by n, n by p, so you get an n by p and a p by q. So it's always that second thing there, that p, that we use as the upper index of our sum. Say from L is equal to 1, you sum from L is equal to 1 to p, of AB, IL, CLJ, this is the definition of matrix multiplication, which is now we need to unwind that even further, as we did before. The sum from L is equal to 1 to p, of the sum from k is equal to 1 to n, of aik, bk, should be bkj, right? Effectively multiplied by clj, right? Or do I really mean j, because then that j is going to coincide with that j, isn't it? Yeah, I've written it IL, okay? So yeah, we should probably, yeah, because I've written IL there, I'm going to put bkl, and then multiply that by clj, okay? And you can see, just by sort of, you could expand this out and then multiply it by CLJ and expand that sum as we did before. This is just going to give you the exact same double sum that we have up there, right? So you can also swap the order of finite double sums, okay? So obviously we have from n equals 1 to p of the sum from k equals 1 to n of all of that. But you can swap the order of those as well. And if you want, you can show that that will keep the sum the exact same. But they're finite sums, so this holds in general for double sums, okay? So we have the sum from k equals 1 to n of the sum from L equals 1 to P of AIK, BKL, CLJ, and that is exactly what we had up here, right? So those two things, they're exactly the same, so we're done, right? Double sums are the same. Double sums are the same. So AB multiplied by C is equal to A multiplied by BC. The matrices ABC. I.e., matrix multiplication is associative. Okay, so a couple more proofs that we need to get done. And then, happy days. Okay, so the next proof is effectively showing that we can distribute multiplication for matrices. So, second last proof here. So here's a theorem. So the distributive law holds for matrices. Distributive law holds also for matrix multiplication. Okay, so it's not the end of the world. Even though matrix multiplication is not commutative, we can still distribute it as we would expect. So that's good, as we do with arithmetic. And this is associative, right? So we're not, we make sacrifices, but we don't make too many. So that's okay. Distributive law, well, laws really hold. Also, for matrix multiplication. Okay, so when the following products and sums make sense, right? Because again, you can't add two matrices unless effectively they're the same size, and obviously the product you already know, and that's defined from today. So when the following products and sums make sense, so whenever they do, so that means just infer what the dimensions of the matrices are going to be, such that like the things, the products and the sums, they all make sense. So when they do make sense, matrix A multiplied by the matrix B plus the matrix C is going to be equal to the matrix A times the matrix B and the matrix A times the matrix C. So you're just distributing this matrix throughout the sum. It's not trivial though, right? You need to prove it because it's not arithmetic where that is just given. Okay, and we have a definition for matrix multiplication, so we can prove it, right? So what we should. Okay, and similarly, A plus B multiplied by C is AC plus BC. Okay, so we can prove these two things. So let's do it. Proof. As we have been doing so far, we're going to consider the ijth element of A, the matrix A multiplied by the matrix B plus the matrix C, which is just going to be this for the subscript ij, right? Which is equal to the sum from k equals 1 to n. And it will be to n because B in this case is, well, I mean, I guess you can make it, like obviously we don't know the dimensions here, so I said it will be to n. But effectively we can make it such that effectively the dimensions work out. So B plus C will have n rows, okay, and A will have n columns, okay. So we just need that to be true for this to be n, okay. Otherwise it'd be a different letter, n, p, q, whatever it is. Just know that it's always going to be effectively, if we have n by n, n by p, the upper limit of our sum, the upper sort of bound of our sum is going to be this variable here, okay. Just remember that. So that's going to be the sum from k equals 1 to n of aik, and then every element, we defined this in the previous video, I believe, of the matrix sum B plus C is given by BKJ plus CKJ. Okay? Okay. Awesome. Okay, and then what we can do is we can just distribute this sum, right? So then what we have is that this sum is equal to the sum from k equals 1 to n of aik bkj, add the sum from k equals 1 to n of aik ckj. And you immediately see this is just by definition ab, and this is by definition ac. So actually, we've shown by definition, effectively, but as a proof, we've used the definition to prove it, that effectively, for matrices a, b, and c with suitable dimensions, a times b plus c is indeed ab plus ac, as you would expect. Okay? So, yeah, that's it, right? Obviously, we can also do the exact same thing the other way around, but just in terms of time, I'm going to not do it. But this argument here as to why this is true is exactly the same. Okay, you just use, and I would advise you do it. You need to be familiar with the matrix multiplication definition. So if you want to familiarize yourself with that, try this proof. Okay, try it out. Try it out. Try and prove that this is true. Okay, because you've proven this is true. So just take the same ideas and really understand what's going on. Okay. Very good. And lastly, we have one more thing that we want to prove, which is the following. Okay, if two matrices multiply to give you the zero matrix. Okay, for two matrices mn, mn, one cannot conclude, so it cannot be concluded from that fact, that one of mn is equal to 0, or is the zero matrix, okay? So just because when I multiply my two matrices together, I get the zero matrix, does not mean that one of my matrices is the zero matrix. So I can't, like, something, this is unfortunately different to arithmetic, because in arithmetic, when I have a product of two numbers, a, b, if it's 0, one of these numbers has to be 0. This is a known fact. So it might be strange to see this, that actually with two matrices, you can have non-zero matrices that multiply to give you a zero matrix, okay? Just the way that matrix multiplication works, okay? And I can convince this to you pretty easily, actually. Even though it's weird to kind of accept it, it's true, right? And it's pretty easy for me to convince that to you, to convince you of that, right? And I can just basically give you an example, and that proves it, right? So yeah, let's just exactly, just prove. Effectively, this is effectively prove it via counterexample, right? You can found a counterexample to the claim that if mn, or disproof by counterexample, right? So when I say it's a proof by counterexample, I really mean it's a disproof by counterexample. So I take the effectively opposite of that statement, which is that if mn is equal to 0 for two matrices mn, then one can conclude that one of mn is 0, and I prove it's wrong, okay? So that was also what we did for the matrix multiplication is commutative, is we assumed it was commutative and found the counterexample. So it's a disproof, really. So disproof by counterexample. So assume mn. So we assume first that if mn is equal to 0 for matrices mn, implies that m equals 0 or n equals 0. Now we can find a counterexample, a suitable counterexample to that claim. Okay? So the counterexample that I came up with, very similar to the counterexample from before. So if we have let m equal 1, 0, 0, 0, okay, again, try and be as simple as possible. If you can include zeros in your counterexamples, it's a lot easier to do matrix multiplication with zeros in the matrix, right? Because you just get lots of zeros in the resultant matrix, you multiply them together. So now in this case, mn is actually the zero matrix, because you get 1 times 0 plus 0 times 1, no, sorry, 1 times 0 plus 0 times 0 doesn't make a difference anyway, but 0. 1 times 0 plus 0 times 1 is 0, 0 times 0 plus 0 times 0 is 0, 0 times 0 plus 0 times 1 is 0. So you get the zero matrix, right? So mn is actually the zero matrix. When you multiply the matrix together, you get the zero matrix, okay? Yet, the most important fact is that none of mn are the zero matrix, okay? Right? So neither are the zero matrix, i.e. none of mn are the zero matrix. So actually, what we assumed is false, right? So if mn equals 0, one cannot conclude. So if the product of the matrices is the zero matrix, that's what I really mean here. It's slightly informal, but that's what I mean. Because you can't get just a scalar out of matrix multiplication, right? Unless you had like a 1-by-1 matrix, but I mean, then it's not, I mean, it is a matrix, but like, it's still, the resultant is still a matrix. It's not just a number 0, right? So you never really get a scalar out of it. But effectively, if you have two matrices that give you the zero matrix and multiply together, one cannot conclude, okay? You cannot conclude that m is equal to 0 or n is equal to 0. So that makes it a lot harder for us to deal with those sorts of equations and things like that. I say equations, but like, if I have two matrices equaling 0, it's a lot harder for us, when you multiply them together, it's a lot harder for us to basically say, well, what does that mean, right? Like, because it doesn't mean that one of them is 0. So it's a lot harder for us to, like, if we were to ever get a condition where we know that two matrices multiplied together does give us a zero matrix, then it's harder for us to make any assumptions, to make any conclusions from that, because we don't know that m or n, that any of them, we don't know for sure that one of the matrices is the zero matrix. It could be, and if it is, it's efficient, because if one of the matrices is the zero matrix, suppose that m is the zero matrix, certainly mn will be the zero matrix. Okay, but we don't know it for sure. So this condition, we cannot work backwards and say that m is 0 or n is 0 effectively, which is bad. I mean, it's bad, but it's also like a fact, right? The way we define matrix multiplication allows this to happen. Okay, so we could change the definition to change this, but again, there are reasons for the definition, and as mathematicians, we've chosen to keep that definition. Okay, that's going to be all for today. Thank you guys very much for watching, and I'll see you guys in the next one. Goodbye.